Hi everyone, my name is Fahad Islam and welcome to my ICRA talk. Today I am presenting Alternative Paths Planner or app for provably fixed time manipulation planning in semi-structured environments. This is joint work with my internship collaborators at NVIDIA. In many applications, robot manipulators operate in semi-structured environments alongside humans or other robots. These environments are largely static, but they may contain some movable obstacles that the robot must avoid. In this video, we show a kitchen environment as an example, where the robot has to pick up the red bowl while avoiding collisions with the blue pitchers and the table. The movable obstacles here are the pitchers, whereas the rest of the environment is static. Manipulation tasks in these environments are often highly repetitive, but require fast and reliable motion planning capabilities. To this end, we propose a novel pre-processing based method called Alternative Paths Planner that provides provably fixed time planning guarantees. Let's break down the problem setup. We have a start configuration S start. We have a goal region G, which is discretized to get a finite set of goals. And we have a semi-static world W. W has two components, WO and WS. WO contains a fixed number of movable obstacles, which in this example are the two blue pitchers. WS represents the static portion of W, which in this example is the ground. So here is the problem statement. Construct an algorithm that guarantees to return a collision-free path for a robot in W from S start to any goal within the goal region within a fixed small time period. Let's look into some of the related work. For semi-structured domains, roadmap-based planning approaches have been very popular historically. They construct a roadmap offline and perform a search at the runtime to find a path. To account for any changes in the environment, some of these methods defer the collision checking operations to the online phase, while other methods repair the pre-computed roadmap at runtime to handle any changes in the environment. Another class of planners exploit previous experiences to speed up search by either using experience-guided heuristics or reusing segments from previously computed paths. While all these approaches do provide significant speedups, they do not provide fixed time planning guarantees. More recently, fixed time planning algorithms were proposed that provide provably fixed time planning guarantees. However, they are only applicable to highly structured or purely static environments. Our approach app extends these approaches to semi-structured domains while still guaranteeing provably fixed time planning. To understand the key idea, let's look at a simple example. We have a start and a goal, some static obstacles shown in gray, and two movable obstacles shown in red. For this environment, if we compute three paths that are separated enough, one of the paths will always be collision free, no matter where the two movable obstacles are located, provided that they are not too close to the start or the goal. So the key idea here is very simple. For each goal in the goal region, plan a set of alternative paths offline such that for any configuration of the movable obstacles, at least one path is collision free. And during online execution, for any given configuration of the movable obstacles, just loop through these paths to find the one which is collision free. Let's see how app computes these paths to provide such a guarantee in the case of two movable obstacles O1 and O2 that could appear anywhere in the dotted region. The static obstacles are shown in gray. App finds the first path y1 by only avoiding the static obstacles. It then constructs an envelope e pi 1 around the path pi 1. An envelope is a set of all obstacle locations that intersect a path. It is computed by inflating the path by the size of the movable obstacle. Next, app finds the second path pi 2 while avoiding the envelope e pi 1. We say that the paths pi 1 and pi 2 are disjoint. Two paths are disjoint if their envelopes do not overlap. Now, for any position of O1, at least one of these paths is guaranteed to be collision free. Next, to account for O2, app needs a third disjoint path. To do so, it constructs envelope e pi 2 around the path pi 2 and attempts to find the third disjoint path by avoiding the two envelopes, but it fails because the path does not exist. To ensure completeness, app needs to compute additional paths. At this point, it bisects one of the envelopes into two child envelopes ER and EL. It finds the third path pi 3 around E pi 2 and ER, finds the fourth path pi 4 around E pi 2 and EL. App now has sufficient paths to handle any configuration of O1 and O2. In the query stage for any given configuration of movable obstacles, app loops over the set of pre-computed paths until it finds a collision-free path, which is the red one in the shown example. It is important to note that while doing so, it does not require any collision checking, which is typically the most computationally expensive operation in motion planning. Instead, it uses the stored envelopes for each path to identify the one which is collision free. And by the definition of an envelope, the path whose envelope does not contain any of the queried obstacle positions is the one which is guaranteed to be collision free. This query phase is very efficient and takes only a few microseconds. In this video, we demonstrate our approach for the mail sorting task. In the shown example, the algorithm must generate plans to pick up the red ball and place it in the cubby shelf while avoiding collisions with the table, the shelf, and the two movable obstacles. We approximate the collision geometry of the robot, the attached ball, and the movable obstacles using spheres. The robot uses the same path in reverse to go back to the start configuration. In this video, we give a rundown of the pre-processing steps for the mail sorting domain and visualize the paths and the envelopes that it computes. The first path is computed from start to goal while avoiding only static obstacles. The second path is computed while avoiding static obstacles as well as the first envelope. Finally, the third path is computed while avoiding the static obstacles and the two envelopes. Here we show all three paths simultaneously. App guarantees that for any configuration of the two movable obstacles in this scene, one of the three paths would be valid at query time. Note that if app cannot find three disjoint paths, then additional paths are computed to maintain this guarantee as was illustrated in the 2D example earlier. In the query stage, app looks up the valid path from a set of pre-computed paths using the obstacle positions stored in the envelopes. The path whose envelope does not contain any of the queried obstacle positions is selected and is guaranteed to be collision free. The three columns in these videos show example queries for which each of the three pre-computed paths were selected by app. For the statistical results, we tested in two tasks, shelving and sorting. In both the tasks, the goal and the movable obstacles are positioned randomly. In the shelving task, the robot has to reach a can in the rear section of the shelf while avoiding collisions with the objects that are in the front section. In the sorting task, the robot has to pick up the objects from a tabletop while avoiding collisions with the nearby objects and then place them in the cubby. App shows 100% success rate for both the tasks with a mean planning time of below 10 microseconds, showing several orders of magnitude speed up in planning time compared to several state-of-the-art planning algorithms. Here we show the experiments in simulation. The task here is to pick up the ball while avoiding collisions with the two pitchers and the ground. In simulation, we achieve a task success rate of 100%. A run is labeled as a success if the robot successfully picks up the ball without collisions with the pitchers or the ground. We also experimented on the real robot with onboard perception. The captions in the video show the current state of the system. The planning happens in between object detection and following trajectory. Note that the planning time is hardly noticeable and is yet mostly consumed in path post processing. To conclude, we developed a manipulation planning algorithm which plans within a provably fixed time of a few microseconds and is applicable to semi structured robot environments. One of the limitations of app is that its pre-processing time can grow drastically if the movable obstacles increase beyond a certain number. To this end, an interesting future direction could be to develop an anytime variant of app which tries to maximize the number of possible queries that it can handle in the available pre-processing time. With that, I conclude my talk. Thank you for attending and I hope you enjoy ICRA this year.